Hey guys, welcome to another video on A-Level Physics P5, and this time we will be doing May-June 2016 P51. So let's get on with it. The student is investigating the characteristics of different light-emitting diodes. Figure 11.1 shows examples of LEDs and the circuit symbol for an LED. Right? Each LED needs a minimum potential difference V across it to emit light. And these are a bit of the theoretics. And there is this book, Cambridge International AS and A-Level Physics by David Sang, Graham Jones, Vrinda Shida and Richard Woodside, and it's pretty great at all of this experiment stuff. So there are these boxes in the middle of chapters which contain details about experiments. I would suggest that you read these if you have not already done so. They are a real big help to me, so you may be able to benefit to an extent as well. Returning back to the question at hand. So, what the student is doing is investigating the relationship between V and the wavelength of the light emitted by the LED for several different LEDs. And it is suggested that the relationship is V into K into lambda raised to power n, and both K and n are constants. And you need to design a lab experiment to test the relationship between V and lambda and explain how your results could be used to determine values for K and n. You should draw a clear-cut diagram to show the arrangement of your equipment and pay attention to the procedure, the measurements, the variable control, the data analysis, and the safety precautions that should be taken. Right? Now regarding the book I was talking about, for example, in this particular experiment, you do need some background theoretical values. So for example, on the chapter about waves, actually the superposition of waves, which is chapter number 14, page 192, for those of you who already have it. I believe the ebooks are all also available at GCE Guide. They've given all these important formulas about the experimental determination of wavelength using the Young double slit experiment and the use of diffraction gratings. The most important thing is to remember the formula. If you use the diffraction grating, the formula is d sine theta in lambda. D is basically the spacing between the grating. Theta is the angle between the undeviated light and whatever light you're taking it against. And n is the order. Like, this is going to make sense if you read the theoretical aspects of this topic. And for the other one, it's lambda is equal to ax over d, where a is slit separation, x is fringe separation, and d is slit to slit distance. So again, you really need the theoretics for this particular topic. And for LEDs, I believe in the electronics topic, they've also introduced it to an extent. It's not all that necessary for this topic, but you do need to know a bit about it. So now back to the actual question. So from what we read, how many variables can we easily deduce from the data that you've given and from the deductions you've already made as to which part of the syllabus this is coming from. There is the obvious voltage and wavelength. Like that seems pretty obvious, right? Is there anything else that you would need to standardize? So how do you know that light is being emitted? Hell, it could be emitted, but it could be very little intensity and would not be visible, or you may need some sort of a standard. So you can use something like an LDR that has been calibrated, or a photometer. So when it gives a particular value of the voltage across it, you know that it is emitting a certain light intensity. So this is a way of standardizing your results, even though it's not exactly standardization of the variable. And obviously you need to carry out this experiment in a dark room, same as with sound experiments, in which you need to carry it out in a quiet room. You need to carry this out in dark room. And usually when they give you those diodes, the wavelength is mentioned, but if it is not mentioned, you can use a diffraction grating, right? So you can have the LDR with the voltage across it, and all of that is basically emitted to a diffraction grating, or more easily through a young double slit, and then you're going to see fringes on the other end, and you're going to basically measure the distance between consecutive fringes using a vernier caliper, and the slit separation would already be given. You'd already be aware of it. It would be given on the slit, and you'd use a meter rule to measure the distance between the slits and the card on which you were observing those fringes, and then you're going to find lambda by lambda is equal to ax over d, right? So these are the basics. About the voltage, you would have a voltmeter around the diode, and what you can do is you can either use a variable power output. You're going to slowly increase the voltage, right? And you would observe that voltage across the diode, and then you're going to stop the moment you see that the LDR is saying that that particular threshold light intensity for which it is saying that the LED is on has been achieved. So there's this thing. Safety precautions: don't touch the diode, it's probably hot. Data analysis is easy. You're just going to have to do with either the normal log or the natural log, okay? So now let's actually do this. Number one thing to do is to draw a diagram that you can actually use. So let's have this. This is light emitting diode. Maybe that is how they drew it. I can't believe I forgot this. Knew something was missing. Right? And I think, personally, I feel that instead of using the variable output, you can use a rheostat. I think, well, actually, in reality, that's a bit easier thing to do. I suppose it doesn't really matter when you're just detailing them out. So we have rheostat. Remember, labeling is so important. You're gonna lose marks for nothing if you don't do it. And over here you have DC power supply, right? And over here, what do you have? You have a voltmeter that is across the LED, and you need this to be labeled as well. Unfortunately, that is not the end of the experimental setup. You need to draw the LDR as well. Now you know, with the LDR and the LED, they have startlingly similar in that there is light coming in and coming out, but the resistor portion is what distinguishes it. So yeah, it was kind of terrible. And this is a sensing circuit. And again, you need a voltmeter. And you need these labeled. So, I guess this is it. If you can manage to make it neater, you should. Everything ought to be labeled. Rheostat, LED, voltmeter, DC power supply, DC power supply. You should also probably put in a switch in both of these. Light dependent resistor, constant resistor, and voltmeter. Right? So, then you're going to write the independent variable is the wavelength emitted by the LED, and the dependent variable is the voltage needed for the LED to start emitting. Now what about the variables you need to standardize? Well, if you think about it, because we're using this to be the sensor device, what are the things you should probably have standardized? Because what this is detecting is basically light intensity. So what are the things that are going to affect light intensity? Yep, distance. So the distance between the LED and the LDR needs to be a constant, and it needs to be very short, because light intensity is something that decreases pretty quickly over distance. So this D needs to be small. Alright, so you need to use LEDs of different wavelength. Sometimes the wavelength is written on the box, but occasionally it is not. And also, to double check and confirm, you may use a young double slit to figure out the wavelength of light being emitted by an LED. An LED can be connected into a circuit with a power supply and switched on. The circuit would be placed pretty close to a young double slit with a screen about a meter away. This experiment to figure out wavelength will be carried out in a dark room. After a few minutes of stabilization, you will observe fringes on the screen. Use a vernier caliper to measure the distance between consecutive fringes and a meter rule to measure the distance between the double slit and the screen. Lambda is A into X into T, and X is a slit separation, and that would be written on the double slit. If it isn't, you may use a vernier caliper, but it will be very difficult to measure. In turn, connect the diodes into circuit A shown in the diagram above. Turn off the switch. Initially, have the rheostat at a very high value, and all of this should be carried out in a dark room. Then slowly decrease the resistance of the rheostat while observing the reading of the voltmeter across the LDR. LDR has a very high resistance in dark and low resistance in the light. A particular value of the voltage will be decided to correspond to the moment the LED was emitting light of a particular minimum intensity, which would be seen as it being on. Stop increasing the rheostat the moment that voltage is registered, and note down the voltage across the LED. Right? I guess I haven't missed out anything. If you don't have an LDR, there are other things you can use, something called a photometer, but I think the LDR is the more commonly found laboratory equipment. Data analysis. Let's see if we take the log. Log V is equal to log K plus N into log lambda, and because lambda is basically, as we said, the independent variable, so this is x. That makes N the gradient, K the y-intercept, and V on the y-axis. So if you plot log over V on the y-axis against log x on the x-axis, and you get a straight line with a positive gradient that does not go through the origin, your relationship is probably valid. And you want to know the value of N is equivalent to the gradient. What about K? C is equal to log K. So K is equal to 10 raised to the power C. Cautions: don't touch the LEDs. Before or after they're on, they're probably really hot. So let's take a look at the marking scheme to see how well we did. So let's see the marking scheme. Lambda is the independent variable, V is a dependent variable. Done. 2 marks. DC power supply, yep, that is important. In series with diode, and method to measure PD, circuit must be correct. Instrument to change PD across LED, example variable power supply, potential divider, or variable resistor. Yep, we used these one. Record wavelength of light of LED from datasheet, or use either Young-Slits or diffraction grating. Slowly increase the potential difference across LED until LED just emits light. Yep. Log V against log lambda is equal to gradient, K is equal to 10. Use of a protective resistor can be shown. Polarity of LED correct in the circuit diagram. Actually, because we used a power supply, it wouldn't really matter, because in a normal power supply, the one I used, it's not shown. However, if it had been this sort of symbol I had used, then this is a positive, and so this should have been facing this side. This would have been the attachment had I used this one. Something I may forget. You may forget if you use a battery next time in this sort of an experiment. Instrument to determine when LED just emits light, example light meter or LDR. Method to use light detector to determine point at which LED emits light. Expression that gives lambda from experimental determination of wavelength. Perform experiment in the dark room, straight line, Again, I forgot about the whole repetition thing. 1, 2, 3, 4, 5, 6 full marks. Stuff I missed out. Repetition, so important. Polarity, I didn't really get a chance to draw that. And this is something you can introduce. A lot of apparatus like a relay and especially in LED is important. In electronics, we specifically read about how we had to use a resistor when using LEDs as output devices because they are really sensitive, right? I think examiner report checking that out is maybe a good idea. Candidates were required to investigate the characteristics of different LEDs, and they were to investigate the relationship between the minimum PD across an LED and the wavelength emitted for several different LEDs. Many candidates were not awarded credit for identifying. They often correctly chose the variables but interchanged them. That is, V was selected as the independent variable, and most of these candidates received partial credit for stating that they would measure the PD across the LED. On this particular question, there was no constant in the given relationship, though many candidates stated current was to be kept constant. 4 marks are available for data collection, correct workable circuit, correct circuit symbols, voltmeters connected in series, not across or no DC source shown. A significant number of candidates correctly placed a variable resistor in the circuit or labeled the power source as variable. Candidates should check the polarity. A mark for additional detail was available for showing the correct polarity of the power supply such that the diode was forward biased. Many candidates thought that a light detector connected to a cathode ray oscilloscope can measure the frequency of light, but this was not awarded credit. Stronger candidates selected a diffraction grating or Young slits, gave good explanations, and gained an additional detail mark for the correct equation to determine the wavelength. When quoting equations, should define all the symbols used and should make the quantity being determined the subject. Practical method of obtaining the minimum PD. Many did not state how they would use a circuit to measure the PD across the diode. It was expected the PD would be increased slowly by the variable power source or by changing the resistance of the variable resistor until the LED just emits light. Candidates often described measuring the PD with a voltmeter, but tended not to explain how the exact point when the LED just emits light was achieved. There are now 3 marks available for data analysis, and the majority of candidates scored the first for identifying a graph to plot, though a few did not convert the quantities to logarithms. Both logarithms to the base 10 and natural logarithms were accepted. Determination of the value of n was often given. We also needed to give the one for k. Minimum 6 marks, maximum, my apologies. Right? So, again, time is something that is really important. Let's just think about it. We have like 75 minutes and 2 questions. So we have approximately 38 minutes for each question. Something to keep in mind. Hopefully you found this to be helpful. Thank you.